Imagine you are standing in a field at night, somewhere on the coast of the Aegean Sea, roughly 2,500 years ago. There are no streetlights, no power lines, and no satellites blinking overhead. The sky above you is so dense with stars that the darkness between them feels like an accident. You can see the Milky Way as a bright river of light pouring across the sky from horizon to horizon, and you are looking up at all of it, every point of light, every slow-moving planet, every streak of a falling star, and you are asking the question that every civilization has eventually asked. What is all of this made of? What are the rules? Why does any of it work the way it does? That question, and every attempt to answer it over the last 25 centuries, is what this video is about. This is the entire story of physics. All of it, from the first person who guessed that matter might be made of tiny invisible pieces, to the particle accelerators that confirmed it, from a man who dropped 2 balls off a tower, to prove Aristotle wrong to the theory that says time itself bends near heavy objects, from a candle flame to the heat death of the universe. We're going to cover the people who figured it out, the arguments they ran, and the questions they still can't answer, including the fact that 95% of the universe appears to be made of something we've never seen, never touched, and can't explain. All of it, slowly, for sleep. And it starts with a guess so good that it took 2,400 years to prove it right. About 2,500 years ago, in the Greek city of Abdera on the northern coast of the Aegean, a philosopher named Democritus proposed an idea that would turn out to be one of the most consequential guesses in the history of human thought. He said that if you take any piece of matter, a stone, a leaf, a drop of water, and cut it in half, then cut the halves in half and keep cutting, you don't keep going forever. Eventually, you reach a piece so small that it can't be cut any further. Eventually, an uncuttable particle. He called it atomos, from the Greek word meaning indivisible. The atom. Democritus didn't invent this idea entirely on his own. His teacher, a philosopher named Leucippus, had proposed the basic framework, but Democritus developed it into a complete worldview. Everything that exists, he argued, is made of atoms and empty space. Atoms differ in shape, size, and arrangement, and those differences explain why stone is hard and water is fluid and fire is. The soul is made of atoms. Thought is made of atoms. The gods, if they exist, are made of atoms. Nothing exists but atoms and the void. This is an extraordinary claim for the 5th century before the Common Era. There were no microscopes, no experiments in the modern sense, no way to see or touch or measure an atom. Democritus arrived at this idea through pure reasoning. He asked what would happen if matter were infinitely divisible, decided the consequences were absurd, and concluded that matter must be made of fundamental pieces. And here is what makes this story remarkable. He was right. Not in every detail. He didn't know about electrons or quarks or the strong nuclear force, but the core claim that matter is made of tiny indivisible units, that the properties of everything you can see and touch emerge from the arrangement and behavior of these units. That claim survived 24 centuries of scrutiny and is now the foundation of chemistry, biology, and physics. Democritus guessed atoms into existence with nothing but his mind, and the guess held. He wasn't alone in this intuition. In India, the Vaisheshika school of philosophy, founded by the sage Kanada around the 6th century before the Common Era, independently proposed that all matter is composed of paramanu, eternal, indivisible particles that combine in specific ways to form the substances we observe. 2 civilizations, separated by thousands of miles and developing without contact, arrived at remarkably similar conclusions about the fundamental nature of matter. The idea kept surfacing because the structure of the world keeps pointing toward it. But Democritus lost the argument in Greece, not because his idea was wrong, but because he was up against the most influential thinker in the history of Western civilization. The philosopher who rejected atoms and replaced them with a system that would dominate physics for the next 1,500 years was a Greek named Aristotle, born in Stagira in 384 before the Common Era. Aristotle was not just a physicist. He was a philosopher, a biologist, a logician, a political theorist, and a teacher. He tutored Alexander the Great. His intellectual range was staggering. He wrote about everything from the movement of stars to the reproductive habits of sea urchins, and he did so with a systematic rigor that made his conclusions feel authoritative even when they were wrong. Aristotle's physics was built on observation and common sense, which is both its strength and its fatal flaw. He watched the world around him and drew conclusions. Heavy objects fall faster than light ones. Obvious if you drop a stone and a feather. Objects in motion come to rest unless something keeps pushing them. Obvious if you push a cart and let go. The Earth is at the center of the universe and everything revolves around it. Obvious if you look at the sky. He divided matter not into atoms but into 4 elements: earth, water, air, and fire. Each element had a natural place. Earth sank to the bottom because its natural place was at the center. Fire rose because its natural place was at the top. Water and air sat in between. Motion, in Aristotle's system, was the process of things seeking their natural place. A rock falls because it's made of earth and earth belongs at the center. Smoke rises because it contains fire and fire belongs at the top. Everything moves toward where it belongs, and when it arrives, it stops. This is wrong, almost entirely wrong, but it is wrong in a way that feels deeply right if you don't have access to controlled experiments, vacuum chambers, or the concept of inertia. Aristotle's physics matched everyday experience so closely that it took over 1,000 years for anyone to seriously challenge it. There's a lesson in that, and it's worth pausing on. The most dangerous kind of wrong is the kind that looks right from where you're standing. Aristotle wasn't stupid. He was arguably the most intelligent person of his era. His conclusions were logical given his observations. The problem was that his observations were limited by the world he could see, a world of friction, air resistance, and gravitational acceleration, all tangled together in ways that made the underlying physics invisible. He saw the surface behavior and built a theory to explain it. The theory was elegant, comprehensive, and wrong. There is a deeper reason Aristotle's physics survived so long, beyond institutional support. His system was comprehensive. It didn't just explain how things move. It explained why they move, where they belong, what they're made of, and how the cosmos is organized. It was a complete worldview from the center of the Earth to the outermost sphere of the stars. Replacing it required not just correcting individual errors but providing an alternative framework that was equally comprehensive. And that took centuries, because the alternative framework, mathematical, experimental, based on measurement rather than reason, had to be invented from scratch. And because Aristotle's authority was so immense, because he was adopted by the Catholic Church as the philosophical foundation for its understanding of the natural world, because his works were preserved and taught in every European university for centuries, his physics became something close to sacred. Questioning Aristotle wasn't just questioning a theory, it was questioning the intellectual order of the Western world. Meanwhile, outside of Europe, physics was progressing. The first person to develop a rigorous experimental approach to optics, to insist that claims about how light behaves must be tested through systematic observation rather than accepted on the authority of ancient texts, was an Arab scholar working in Cairo in the early 11th century named Ibn al-Haytham, known in Latin sources as Alhazen. His 7-volume book of optics, written around 1015, was one of the most important scientific works of the medieval period. He demonstrated that vision works by light entering the eye, not by the eye emitting rays, overturning a belief held by both Greek and Islamic scholars for centuries. He studied the behavior of light through lenses and curved mirrors with a methodical precision that was centuries ahead of its time. He built a camera obscura, a dark room with a small hole in one wall, and demonstrated that the image projected through the hole is inverted, proof that light travels in straight lines. He investigated why the moon appears larger near the horizon than at its zenith, and correctly identified the cause as a psychological illusion rather than a physical magnification. He studied the rainbow and proposed a theory of its formation that, while incomplete, was based on the refraction of light through water droplets, an approach that Roger Bacon and others would later refine. He investigated refraction, the bending of light as it passes from one medium to another, and he insisted, repeatedly and explicitly, that scientific claims must be verified by experiment. Ibn al-Haytham didn't just study light. He established a method. The method says, propose a hypothesis, design an experiment to test it, observe the results, and accept what the results tell you, even if it contradicts what you believed before you started. That method, formalized and refined over the following centuries, would become the foundation of modern science. Europe would eventually call it the scientific method, often crediting Francis Bacon or Galileo for its invention. But Ibn al-Haytham was doing it 200 years before Bacon was born. But none of these ideas, Greek atomism, Islamic experimental optics, Indian atomic theory, could dislodge Aristotle from his throne in European thought. That would require someone willing to fight the most powerful institution on earth over the right to describe how things fall. That person was born in Pisa in 1564, and his fight would cost him his freedom. The first person to systematically dismantle Aristotle's physics through controlled experiment, and to insist that the laws of nature must be written in mathematics rather than philosophy, was an Italian astronomer and physicist named Galileo Galilei. He is sometimes called the father of modern physics, and while that title oversimplifies the contributions of everyone who came before him, it captures something real about the shift he represented. Before Galileo, physics was a branch of philosophy. After Galileo, physics was a science. The story usually told about Galileo involves the Leaning Tower of Pisa. According to the legend, he climbed to the top of the tower and dropped two balls of different weights simultaneously, showing that they hit the ground simultaneously, disproving Aristotle's claim that heavier objects fall faster. Whether or not the tower experiment actually happened, the historical evidence is thin, and the story may have been embellished or invented. The conclusion is genuine, and Galileo did demonstrate it through careful experimentation. What Galileo actually did, which was more important than any single demonstration, was measure how things fall. He rolled balls down inclined planes, timing their descent with water clocks and his own pulse. He varied the angle of the incline and the weight of the balls. And he discovered something that Aristotle's physics couldn't explain. All objects accelerated identical rates when falling, regardless of their weight. A cannonball and a musket ball, dropped from equal height in a vacuum, hit the ground at one instant. This doesn't match everyday experience, because everyday experience includes air resistance. A feather falls slower than a stone because the air gets in the way, not because the feather is lighter. Galileo had the insight to see past the surface and ask what would happen in the absence of air, what the pure underlying law actually is. And the law is, acceleration due to gravity is constant, weight doesn't matter. Aristotle was wrong, and Galileo could prove it. He also discovered something about motion that would take 2 centuries to fully appreciate. Galileo noticed that a pendulum of a given length always swings with a constant period, regardless of how wide the swing is. He reportedly timed pendulums using his own pulse while sitting in a cathedral, watching a lamp swing after it was bumped. He studied projectile motion and showed that the path of a thrown object is a parabola, a specific mathematical curve. He demonstrated that the distance a falling object travels is proportional to the square of the time it has been falling, the first mathematical law of motion ever discovered. Every one of these results contradicted Aristotle. Every one of them was confirmed by experiment. Every one of them required measuring rather than philosophizing. He also made another discovery that was even more dangerous. Using a telescope he had built himself, not invented but significantly improved from a Dutch design, he turned it toward the sky and saw things no human being had ever seen. He saw that the moon's surface isn't smooth but covered in mountains and craters just like the Earth. He saw that Venus goes through phases, like the moon, which only makes sense if Venus orbits the sun, not the Earth. He saw that the Milky Way, which looks like a continuous band of light to the naked eye, is actually composed of countless individual stars, too faint to resolve without magnification. And he looked at Jupiter and saw 4 small objects orbiting it, moons. If Jupiter had moons orbiting around it, then not everything in the universe orbits the Earth. The geocentric model, Aristotle's model, the Church's model, had a visible telescopic crack in it. Galileo published his findings in a book called Dialogue concerning the 2 chief world systems, which presented the case for the heliocentric model, the idea that the Earth orbits the Sun. He structured the book as a dialogue between 3 characters, one of whom defended the geocentric view and was named Simplicio, a name that carried unfortunate connotations of simplicity. The Pope, who had previously been sympathetic to Galileo, took the naming as a personal insult. the Inquisition summoned Galileo to Rome. He was tried, found vehemently suspect of heresy, and forced to recant his support for the heliocentric model. He spent the rest of his life under house arrest, forbidden from publishing. He was 69 years old. He went blind in his final years but continued working, dictating his last book, Discourses and Mathematical Demonstrations, relating to two new sciences, to his students. That book, published in 1638 while Galileo was still under house arrest, laid the foundations for the science of mechanics, the study of how objects move under the influence of forces. It was smuggled out of Italy and published in the Netherlands. The trial itself was political as much as it was theological. Galileo had allies within the Church, including cardinals who privately agreed with his conclusions. The Pope, Urban VIII, had previously encouraged Galileo's work, as long as it was presented as hypothesis rather than fact. The dialogue pushed past that boundary. Galileo presented the heliocentric model not as a possibility, but as the truth, and he put the Church's official position into the mouth of a character whose name suggested he was a simpleton. The political protection evaporated. The recantation was humiliating. Galileo, 70 years old and ailing, knelt before the Inquisition and formally declared that the earth does not move. The legend says he muttered, "and yet it moves," under his breath afterward. The legend is almost certainly false, but it captures a truth about the situation. Forcing a man to say something doesn't make it true, and the earth kept moving regardless of what any institution required anyone to say about it. Think about that for a second. The man who proved that objects fall at equal rates regardless of weight, who discovered the moons of Jupiter, who insisted that physics must be mathematical and experimental, spent the last decade of his life imprisoned in his own home for the crime of describing the universe accurately. The Church eventually acknowledged that Galileo was right. It took them 359 years. The formal rehabilitation happened in 1992. There is a line that runs from Galileo through every physics experiment conducted since. The line says, "Don't tell me what you think should happen. Show me what happens when you measure it. If the measurement contradicts the theory is wrong, no matter how elegant or ancient or authoritative it is." That principle, the authority of measurement over the authority of tradition, is the foundation of modern science. It sounds obvious now. It wasn't obvious in 1633. Galileo's legacy isn't any single discovery, though any single one would have been enough to make him immortal. His legacy is the method. He demonstrated that you can learn things about the universe by measuring, by quantifying, by translating physical phenomena into numbers, and then finding the patterns in those numbers. That approach, mathematical, experimental, skeptical of authority, is the engine that would drive the next 4 centuries of physics. And the person who took that engine and built the most powerful machine in the history of science was born on Christmas Day, 1642, in a small farmhouse in Lincolnshire, England. His father had died 3 months before his birth. He was premature, so small that his mother said he could have fit inside a quart mug. He grew up quiet, solitary, and by every account, difficult to be around. His name was Isaac Newton, and what he did during a single 2-year stretch would reshape humanity's understanding of the universe more than any comparable period in history. In 1665, when Newton was 23 years old, the Great Plague swept through England. Cambridge University closed. Newton went home to Woolsthorpe Manor, the family farmhouse, and spent the next 2 years in near total isolation. What he produced during that isolation is one of the most extraordinary bursts of creative output in human history. He developed calculus, the mathematics of continuous change. Think about what that means. Before calculus, mathematics could describe things that are fixed: the length of a line, the area of a circle, the volume of a sphere. With calculus, mathematics could describe things that are changing: the speed of a falling object at each instant, the slope of a curve at each point, the way a population grows or a temperature drops over time. Physics is the study of change, of motion, of forces, of energy flowing from one form to another. Calculus is the language that makes it possible to describe change precisely. Newton didn't just invent a tool, he invented the language his physics would be written in. Newton didn't just affine, not the version we use today, that would be refined by Leibniz independently and argued over for decades. but the core ideas of differentiation and integration, the mathematics of continuous change. He performed experiments with prisms, demonstrating that white light is composed of a spectrum of colors, not altered by the prism, but separated by it. He began formulating his theory of gravity, and he worked on the laws of motion that would eventually become the foundation of classical mechanics. All of this, alone, in a farmhouse. At 23, during a plague. The apple story is probably not true in the way it's usually told. Newton likely didn't have an apple fall on his head and suddenly understand gravity, but he did, by his own account, observe an apple falling and begin thinking about whether one force that pulls the apple to the ground might extend all the way to the moon, whether the moon is, in a sense, falling toward the Earth constantly, but moving forward fast enough that it keeps missing. That insight, that the same force governs the apple and the moon, is the unifying idea of Newtonian gravity, and it was revolutionary. He didn't publish right away. Newton was notoriously secretive, notoriously competitive, and notoriously afraid of criticism. He sat on his results for nearly 20 years. It took the astronomer Edmund Halley visiting Newton in 1684, asking him what shape a planet's orbit would be under an inverse square force law, and Newton casually answering an ellipse, and then admitting he had already worked out the proof to set the publication in motion. Halley, recognizing the magnitude of what Newton had, essentially begged him to write it up and funded the publication himself. The result was the Philosophia Naturalis Principia Mathematica, the Mathematical Principles of Natural Philosophy, published in 1687. It is arguably the most important scientific book ever written. In it, Newton presented 3 laws of motion and the law of universal gravitation, and from those 4 statements he derived the orbits of the planets, the tides, the paths of comets, the precession of the equinoxes, and the shape of the Earth. The 3 laws are deceptively simple. First, an object at rest stays at rest, and an object in motion stays in motion, unless acted on by an external force. This is the law of inertia, and it directly contradicts Aristotle, who believed that motion required a continuous cause. Newton said no, motion is the natural state, it's stopping that requires explanation. Second, force equals mass times acceleration, F equals mass equals A, end 3 letters. One of the most powerful equations ever written. This is the equation that makes physics quantitative. It says that if you know the force on an object and you know its mass, you can calculate exactly how it will accelerate. Every engineering calculation, every rocket trajectory, every structural analysis uses this equation, or something derived from it. Every time an engineer designs a bridge, every time a ballistics expert calculates a trajectory, every time a space agency plots a course to Mars, they are using F equals ma below. The equation is so embedded in modern engineering that it's easy to forget how revolutionary it was. Before Newton, forces were understood qualitatively. This thing pushes harder than that thing. After Newton, forces were understood quantitatively. This thing pushes with exactly this much force, producing exactly this much acceleration in exactly this much mass. The shift from qualitative to quantitative understanding is the shift from philosophy to physics. Third, for every action, there is an equal and opposite reaction. Push on a wall, and the wall pushes back on you. The thrust of a rocket comes from exhaust pushing backward. The reaction pushes the rocket forward. Forces always come in pairs. And then gravity. Every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. The same equation that describes why your coffee sits on the table also describes why Jupiter orbits the Sun. One law, universal, applying to everything from grains of sand to galaxies. Standing inside that system for the first time, seeing how 4 statements could generate the motion of every planet and every projectile and every tide, I remember thinking, this is what understanding looks like. Not memorizing facts, not following rules. Understanding. The feeling that you can see why the universe does what it does, and that the reason is simple. That feeling is what Newton gave the world. He showed that the universe operates according to laws that are expressible in mathematics, that those laws are universal, and that they can be discovered through a combination of experiment and reasoning. Before Newton, the motions of the planets were catalogued. After Newton, they were explained. The difference is immeasurable. The Principia didn't just explain how planets move, it explained why they move the way they do. Kepler, a generation before Newton, had discovered 3 empirical laws of planetary motion: that orbits are ellipses, that planets sweep equal areas in equal times, that the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. These were patterns Kepler found by fitting data. He didn't know why they were true. Newton derived all 3 of Kepler's laws from his single law of gravity. The patterns weren't coincidences, but consequences of a single gravitational law. He also explained the tides. The tides are caused by the differential gravitational pull of the Moon and Sun on different parts of the Earth. Newton's theory predicted this quantitatively. He explained the precession of the equinoxes, the slow wobble of the Earth's axis, which is caused by the gravitational pull of the Sun and Moon on the Earth's equatorial bulge. He calculated the shape of the Earth itself, predicting that it should be slightly flattened at the poles due to its rotation. Measurements confirmed this. The Principia was received with a mixture of awe and resistance. On the continent, followers of the French philosopher René Descartes objected to Newton's concept of gravitational attraction across empty space. Descartes had proposed that the planets are carried along by invisible vortices of matter, swirling around the Sun. Gravity, acting at a distance with no physical medium between the objects, seemed to Descartes' followers like a return to medieval mysticism. Even Newton was uncomfortable with it. He wrote that the idea of one body acting on another through a vacuum, without any intermediary, was so great an absurdity that I believe no man who has in philosophical matters any competent faculty of thinking can ever fall into it. He knew his theory described what gravity does. He didn't claim to know how it does it. That question, the mechanism of gravity, would wait for Einstein. One theory, one force, and one equation, and from it, the motion of everything from cannonballs to comets and comets. Halley used Newton's equations to calculate the orbit of a comet he had observed in 1682. The equations predicted it would return in 1758. It did, right on schedule, 16 years after Halley's death. The comet was named after him. It returns every 75 to 79 years, and last appeared in 1986. It will return again in 2061. Newton's equations predicted the comet's return across centuries with precision that Aristotle's philosophy could never have achieved. Newton lived until 1727. He spent his later years running the Royal Mint, persecuting counterfeiters with surprising zeal, and feuding with Leibniz over who had invented calculus first. The feud consumed the last decades of both men's lives and damaged the development of British mathematics for a century. Newton was not a kind person. He was brilliant, vindictive, secretive, and probably difficult to be around in every conceivable way. But what he built during those 2 plague years, and what he refined over the decades that followed, is the most successful scientific framework in human history. For the next 200 years, Newtonian physics would explain virtually everything physicists could measure. And that is worth sitting with for a moment. One person, working alone during a plague, produced a framework that would accurately describe the motion of every object in the universe for the next 2 centuries, not approximately, exactly. When astronomers discovered the planet Neptune in 1846, they found it by calculating where Newton's equations said it should be and pointing a telescope at that spot. The planet was there. Newton's equations had predicted the existence of a world nobody had ever seen, based on the wobbles it caused in the orbit of Uranus. That is the power of a good theory. It tells you things you didn't know to ask. And then it broke. But that breaking wouldn't come for a while. First, physics needed to understand something that Newton barely touched: electricity. If you are still with me, what comes next shifts from the motion of planets to the sparking of wires, from gravity to magnetism, from a solitary genius in a farmhouse to a self-taught bookbinder's apprentice who couldn't do algebra but could see magnetic fields in his mind. The next chapter of physics is the chapter that gave us the modern world. The first systematic study of electricity was conducted by a printer, a writer, a diplomat, and a kite flyer from Philadelphia named Benjamin Franklin. In the 1740s, Franklin became fascinated with electrical experiments that were being demonstrated as parlor tricks across Europe. He began conducting his own experiments and quickly moved beyond parlor tricks into genuine science. His famous kite experiment, flying a kite in a thunderstorm to demonstrate that lightning is electrical in nature, may or may not have happened exactly as described, but the conclusion was correct, and Franklin demonstrated it through other means as well. Lightning is electricity. The force that makes your hair stand up after rubbing a balloon is that force that splits trees and sets buildings on fire. The difference is only in scale. Franklin also introduced the terminology we still use. He defined positive and negative charge. He proposed that electricity is a single fluid that flows from positive to negative, and he invented the lightning rod, a practical application that saved countless buildings and lives. He was the first person to demonstrate that electricity isn't a laboratory curiosity, but a fundamental force of nature, as fundamental as gravity and far more versatile. But understanding what electricity actually is took much longer. For most of the 18th century, electricity was treated as a kind of fluid, an invisible substance that flows through certain materials and accumulates in others. Some materials, like metals, conduct the fluid easily. Others, like glass and rubber, resist it. Objects with an excess of the fluid repel each other. Objects with a deficit attract objects with an excess. This fluid model captured the behavior well enough for practical purposes, but it didn't explain what the fluid was, why some materials conduct it and others don't, or what the connection might be between electricity and the other forces of nature. That last question, the connection between electricity and other forces, turned out to be the key to everything that followed. Because electricity, it turned out, was not alone. It had a companion, magnetism, and the relationship between them would reshape physics more thoroughly than any discovery since Newton. But Franklin's understanding was still descriptive. He could say what electricity does. He couldn't explain how it works, or what connects it to magnetism, or what either of them has to do with light. Those connections would take another century to discover, and the person who made the crucial breakthrough didn't have a university education, couldn't write a mathematical equation, and spent his early career binding books. The physicist who discovered electromagnetic induction, who showed that a changing magnetic field creates an electric current and thereby made possible every electric motor and generator on Earth, was a working-class Englishman named Michael Faraday, born in 1791 in Newington Butts, south of London. Faraday's father was a blacksmith who was often too ill to work. The family was poor. Faraday received only a basic education and at 14 was apprenticed to a binder. He bound books and he read them, especially the articles on science in the Encyclopaedia Britannica and a chemistry textbook by Jane Marcet. He attended public lectures by the chemist Humphrey Davy at the Royal Institution, took detailed notes, bound those notes into a book, and sent the book to Davy as a job application. Davy hired him as a laboratory assistant. From that position, with no formal mathematical training, Faraday rose through the Royal Institution over the next decade. He discovered benzene. He liquefied chlorine. He invented an early form of the Bunsen burner. He was made a Fellow of the Royal Society. And then he turned his attention to the relationship between electricity and magnetism, a question that had been nagging at physicists since a Danish physicist named Hans Christian Ørsted had noticed, in 1820, that an electric current deflects a compass needle. Electricity and magnetism were connected. But how? Faraday became one of the greatest experimental physicists in history, and his answer to that question changed the world. His key discovery came in 1831. He showed that moving a magnet through a coil of wire produces an electric current in the wire. No battery, no chemical reaction, and just motion and magnetism, creating electricity. This is electromagnetic induction, and it is the principle behind every power plant on Earth. Every coal plant, every gas plant, every nuclear plant, every hydroelectric dam, every wind turbine, all of them work that way. They spin a magnet inside a coil of wire. The spinning magnet creates a changing magnetic field. The changing magnetic field creates an electric current. Faraday's discovery, made in a basement laboratory with hand-wound coils and horseshoe magnets, is the mechanism that powers civilization. The practical consequences took decades to develop. Edison's power stations, Tesla's alternating current systems, the entire electrical grid. All of them are engineering elaborations of the principle Faraday demonstrated in 1831. One experiment, one insight, and from it, the electrification of the world. When you flip a light switch, the electricity flowing through the wire was generated by a magnet spinning inside a coil, somewhere in a power station, using the principle Faraday discovered in his laboratory. Faraday also introduced a concept that would prove even more important than induction. He proposed that electric charges and magnets don't act on each other across empty space through some mysterious force at a distance. Instead, they create fields, invisible structures that fill the space around them and transmit the force through the field. An electric charge creates an electric field. A magnet creates a magnetic field. The fields are real, physical things, even though you can't see them, and objects interact not by reaching across space, but by interacting with the fields at their location. This idea, that forces are transmitted by fields rather than acting instantaneously across empty distance, is one of the deepest conceptual shifts in the history of physics. Newton's gravity acted at a distance. The sun pulls the earth without anything in between. Faraday said no, there's something in between, and the field is in between. And the field is what carries the force. Faraday was also the greatest scientific communicator of his era. He gave public lectures at the Royal Institution that were legendary for their clarity and excitement. His Christmas lectures, started in 1825 and still running today, made science accessible to general audiences. He could explain electromagnetic induction to a room full of people who had never heard the term, using nothing but a magnet, a wire, and his extraordinary gift for analogy. There is something poignant about Faraday's position in the history of physics. He could see the truth of electromagnetic fields more clearly than anyone alive. He understood intuitively that the fields were real and fundamental, that they were the key to understanding how forces work. But he lacked the mathematical language to express what he saw. He was like a poet who speaks a language that has no written form, fluent in understanding but unable to write it down in the symbols that other physicists required. Faraday couldn't express this mathematically because he didn't have the mathematical training. He described his ideas in words and drawings. His famous iron filing diagrams showing magnetic field lines are still used in physics textbooks today. He could see the patterns. He couldn't write the equations. That job would fall to someone else. And what that person produced, using Faraday's physical intuition as the foundation, would turn out to be one of the most beautiful and consequential sets of equations in all of science. But first, physics needed to understand heat. Between Faraday's work in the 1830s and the great unification that was coming, a different branch of physics was developing that would transform both engineering and philosophy. Thermodynamics, the study of heat and energy, began as a practical problem, how to make steam engines more efficient, and ended by revealing one of the most fundamental and unsettling facts about the universe. The origins of thermodynamics are refreshingly practical. The question that launched an entire branch of physics was not philosophical or abstract. It was this: how can we make steam engines work better? In the early 19th century, the Industrial Revolution was transforming Britain, and steam engines were its driving force, powering factories, pumping water from mines, and beginning to pull trains along iron rails. The engines worked, but they were inefficient. Most of the heat from burning coal was wasted, escaping into the air rather than doing useful work. Engineers wanted to know, is there a limit to how efficient an engine can be? Is perfect efficiency possible, or is some waste inevitable? The first person to analyze this question with mathematical rigor was a French military engineer named Sadi Carnot, who published a short but revolutionary paper in 1824 at the age of 27. Carnot showed that no engine can be perfectly efficient. No matter how cleverly you design it, some energy is wasted, converted into heat that you can't use. There is a fundamental limit on how much useful work you can extract from a given amount of heat, and that limit depends only on the temperatures involved. Carnot died of cholera at 36, largely unknown. His work was rediscovered and extended by the physicist who gave entropy its name. Rudolf Clausius, working in Germany, introduced the concept in 1850 that Carnot had sensed but couldn't name. Clausius called it entropy. Entropy is, roughly, a measure of disorder. A neatly organized desk has low entropy. A desk covered in scattered papers has high entropy. An ice cube has low entropy. A puddle of warm water has high entropy. Clausius saw that energy has a direction. Heat flows from hot to cold, never the other way. You can refrigerate your kitchen, but only by pumping the heat somewhere else, using energy in the process. You can't make heat flow uphill for free. That asymmetry, that directionality, is what the second law captures, and Clausius formulated what is now called the second law of thermodynamics. In any closed system, entropy never decreases. It can stay constant, it can increase, and it can never go down. This sounds like a tidy rule about heat engines. It is actually a statement about the fate of the universe. If entropy always increases, if disorder always grows, then the universe is moving in a direction. It's moving from order to disorder, from structure to smoothness, from hot spots and cold spots to a uniform, lukewarm saneness. Given enough time, and the universe has plenty of time, every star will burn out. Every temperature difference will equalize. Every pocket of useful energy will dissipate into useless, evenly distributed warmth. The universe will reach a state of maximum entropy, a state where nothing interesting can ever happen again. This is sometimes called the heat death of the universe, and it is the logical conclusion of the second law of thermodynamics applied to the cosmos as a whole. We're not close to it. The universe is roughly 14 billion years old and has trillions of sheedians of years of stellar burning ahead of it. But the direction is set. Entropy only goes up. The physicist who gave entropy its deepest explanation was an Austrian named Ludwig Boltzmann, working in the second half of the 19th century. Boltzmann showed that entropy isn't a mysterious abstract quantity. It's a counting problem. A high entropy state is a state that can be achieved by many different arrangements of atoms. A low entropy state can only be achieved by a few specific arrangements. The reason entropy increases isn't that there's a law forcing it to increase. It's that there are overwhelmingly more ways for things to be disordered than for things to be ordered. So disordered states are overwhelmingly more waived for popularly. Boltzmann's approach was profoundly democratic. He didn't ask what any individual atom is doing. That question, with trillions of atoms, is impossibly complex. He asked what the most probable behavior of the collection is. He treated physics as statistics, and the statistical answer is that systems overwhelmingly tend toward the most probable state, which is the state with the most possible arrangements, which is the disordered state. It's like shuffling a deck of cards. There's exactly one arrangement that puts them in perfect order. There are trillions of arrangements that look random. Shuffle the deck and you'll get a random-looking result, not because randomness is a force, but because the random arrangements vastly outnumber the ordered ones. Boltzmann's insight was brilliant and is now universally accepted. During his lifetime, it was controversial. Many physicists, including some of the most prominent in Europe, didn't believe that atoms existed, and Boltzmann's entire framework depended on atoms. The resistance was fierce and personal. Boltzmann suffered from depression and what may have been bipolar disorder. In 1906, during a family vacation, he hanged himself. He was 62 years old. Within a few years of his death, the existence of atoms was confirmed beyond any reasonable doubt, and his work was recognized as foundational. The equation relating entropy to the number of microstates is engraved on his tombstone, S equals K log W. Except it's written in words on his gravestone, and the K is now called Boltzmann's constant in his honor. There is something unbearable about that timeline. The man who explained entropy, who showed why the universe runs in one direction, who connected the behavior of heat to the statistics of atoms, died believing his life's work had failed. He was wrong. It hadn't failed. The world just hadn't caught up yet. If you're drifting off, that is fine. The entropy of the universe doesn't mind. Boltzmann's equation sits quietly on his gravestone in Vienna, undisturbed by the passage of time, undisturbed by the slow increase of the very quantity it describes. The tombstone itself is subject to the second law. The stone will weather, the letters will fade, the inscription will eventually become illegible. But the law the inscription describes will outlast the stone, and the universe, and everything else. Some truths are like that. They describe not what happens in any specific case, but what must happen in general, over time, across all possible configurations. Entropy is patient. It doesn't rush. It doesn't care about individual atoms or individual events. It cares about the overwhelming weight of probability, which pushes everything, slowly and inexorably, toward the most probable state, and the most probable state is the one where nothing interesting is happening. It'll keep increasing whether you're awake or not. But if you're still with me, what comes next is the moment when electricity, magnetism, and light all turned out to be one thing. And the person who showed it did it with 4 equations that fit on a single line. The mathematician and physicist who unified electricity, magnetism, and light into a single theory, producing what Einstein later called the most profound and the most fruitful that physics has experienced since the time of Newton, was a Scottish physicist named James Clerk Maxwell, born in Edinburgh in 1831. Maxwell was, by all accounts, a quiet and generous man, utterly unlike Newton in temperament. He was born into a wealthy Scottish family, educated at Edinburgh and Cambridge, and showed mathematical brilliance from childhood. He published his first scientific paper at 14. He worked on a range of problems, from the rings of Saturn to color perception to the statistical distribution of molecular speeds. But his electromagnetic theory is what made him immortal. Maxwell took Faraday's physical intuition, the fields, the lines of force, the invisible structures filling space, and translated it into precise mathematical language. The result was a set of 4 equations, now called Maxwell's equations, that describe how electric and magnetic fields behave, how they're created by charges and currents, and how they interact with each other. Those 4 equations contain a surprise. When you manipulate them mathematically, they predict the existence of waves, ripples in the electric and magnetic fields that propagate through space at a specific speed. Maxwell calculated that speed and found it matched the measured speed of light almost exactly. The conclusion was inescapable. Light is an electromagnetic wave. The light coming from a candle, the infrared warmth from a fire, the radio waves from a transmitter, the X-rays from a medical scanner, the gamma rays from a nuclear reaction. They're all one phenomenon. They're all electromagnetic waves, differing only in frequency. Maxwell unified optics, electricity, and magnetism in one stroke. The beauty of Maxwell's equations is a topic physicists return to again and again. The equations are symmetric in a deep mathematical sense. They reveal connections between electric and magnetic phenomena that are hidden in everyday experience, but fundamental to the structure of reality. Swap the roles of electricity and magnetism in certain ways, and the equations look almost unchanged. That symmetry isn't decorative. It reflects something true about how the universe works. The unification is one of the supreme achievements of human intelligence. 3 apparently different phenomena, the spark from a doorknob, the pull of a compass needle, the light from a star, turned out to be 3 manifestations of a single underlying reality. The fields that Faraday could see but couldn't describe mathematically, Maxwell described with 4 equations so compact and so complete that they've never been revised. Every electromagnetic phenomenon discovered since Maxwell, radio, television, radar, microwaves, fiber optics, Wi-Fi, was already contained in those equations, waiting to be found. And then those same equations contained something else, something that nobody expected and that would eventually break physics open. Maxwell's equations predicted that electromagnetic waves travel at the speed of light, always, regardless of how fast the source is moving, regardless of how fast the observer is moving. The speed of light isn't relative to anything. It's a universal constant. Nobody appreciated the full implications of that prediction for 40 years. Maxwell himself died of cancer in 1879 at the age of 48, never knowing that his equations contained the seeds of a revolution that would overturn Newton's absolute space and time. Einstein would later say that his entire theory of special relativity was a consequence of taking Maxwell's equations seriously, of accepting that if the equations say the speed of light is constant, then time and space must adjust to accommodate that fact. That prediction seemed innocuous in 1865. It would turn out to be a bomb with a 50-year fuse, because if the speed of light is truly constant, if it doesn't change no matter how fast you're moving, then something else has to change instead. Something that everyone assumed was fixed and absolute and beyond question, time. But that revelation was still decades away, and between Maxwell's equations and the revolution they would eventually trigger, something went wrong with classical physics. Something small, something that should have been easy to explain, something involving the color of light emitted by hot objects. It became known as the ultraviolet catastrophe, and it was the crack in the foundation that brought the entire building down. Classical physics. Newton's mechanics, Maxwell's electromagnetism, thermodynamics, was extraordinarily successful. By the end of the 19th century, some physicists genuinely believed that the fundamental laws of nature had been discovered, and all that remained was to measure things more precisely. Lord Kelvin, one of the most prominent physicists of the era, reportedly said that physics was essentially complete, except for two small clouds on the horizon. Those two clouds would turn out to be relativity and quantum mechanics, and together they would demolish the entire classical framework. The first cloud was the ultraviolet catastrophe. When you heat an object, a piece of iron, say, it glows. At lower temperatures, it glows red. Hotter, it glows orange, then yellow, then white, then blue-white. The color of the glow corresponds to the frequency of the light being emitted. Classical physics, using Maxwell's equations and the laws of thermodynamics, predicted how much light an object should emit at each frequency. The prediction was catastrophically wrong. Classical theory predicted that as the frequency increased, the amount of energy emitted should increase without limit, approaching infinity in the ultraviolet range and beyond. A hot piece of iron should, according to classical physics, emit infinite energy at high frequencies. It should glow with the intensity of a nuclear explosion. It obviously doesn't. This was the ultraviolet catastrophe, a case where the best theory in physics produced a prediction that was not just slightly off but infinitely wrong. The person who resolved it didn't want to. Working in Berlin at the turn of the 20th century, a physicist named Max Planck found a mathematical fix for the catastrophe. He proposed that energy isn't emitted or absorbed continuously, in any amount, the way classical physics assumed. Instead, energy comes in discrete chunks, which he called quanta. Each quantum has an energy proportional to its frequency. At high frequencies, the quanta are large, and it becomes statistically unlikely for an object to emit them. This suppresses the high-frequency emission and prevents the catastrophe. The size of each quantum is tiny. For visible light, a single quantum, a single photon, though that word wouldn't be coined for another quarter century, carries an almost inconceivably small amount of energy. But the discreteness matters. Without it, the mathematics predicts nonsense. With it, the mathematics matches experiments perfectly. Planck published his result on December 14, 1900. That date is often cited as the birthday of quantum mechanics, though nobody at the time, including Planck, realized they were witnessing a birth. Planck didn't believe his own solution. He called it an act of desperation and spent years trying to reconcile it with classical physics. He couldn't. The quanta were real, and energy doesn't flow like water. It comes in drops, and that one fact, that energy is quantized, would grow over the next 3 decades into the strangest, most successful, and most philosophically disturbing theory in the history of science. But before quantum mechanics could develop, a 26-year-old patent clerk in Bern, Switzerland, was about to publish 4 papers in a single year that would each independently have been enough to make a career. Together, they reshaped physics from the ground up. In 1905, a young physicist working at the Swiss Patent Office, a man who had failed to find an academic position and was reviewing patent applications for a living, published 4 papers that are now collectively known as the Miracle Year Papers. His name was Albert Einstein. The first paper explained the photoelectric effect, the observation that light can knock electrons out of metal surfaces. Einstein proposed that light itself is quantized. It comes in packets, later called photons, each carrying a specific amount of energy. This was a radical extension of Planck's idea. Planck had quantized the emission and absorption of energy. Einstein quantized light itself. That paper would eventually win him the Nobel Prize, though not until 1921. The second paper provided definitive evidence for the existence of atoms. Einstein analyzed Brownian motion, the random jiggling of tiny particles suspended in a fluid, and showed that the jiggling was caused by invisible atoms bumping into the particles. His mathematical analysis allowed physicists to calculate the size of atoms and gave Boltzmann's statistical mechanics a concrete, measurable foundation. After Einstein's paper, the reality of atoms was no longer debatable. The third paper introduced special relativity, and here is where things get genuinely strange. Einstein arrived at special relativity not through experiment but through thought experiments. He famously imagined chasing a beam of light. If you could run alongside a light beam at the speed of light, what would you see? Maxwell's equations say a light beam is a self-sustaining oscillation of electric and magnetic fields. If you were moving alongside it at a constant speed, the oscillation would appear frozen, a static pattern of electric and magnetic fields just sitting there. But Maxwell's equations don't allow such a static solution. A frozen light beam is impossible. Therefore, Einstein concluded you can't catch up to a light beam. The speed of light must be constant for everyone, regardless of their motion. That reasoning, rigorous, abstract, based on the internal consistency of physical laws rather than on any particular experiment, was characteristic of Einstein's style. He thought in pictures, he imagined scenarios, he followed the logic wherever it led, even when it led to conclusions that contradicted common sense. Einstein started with two assumptions. First, the laws of physics are constant for everyone moving at a constant speed. There is no way to tell whether you're moving or standing still, as long as your motion is smooth and constant. Second, the speed of light is constant for everyone, regardless of how fast they're moving. Maxwell's equations had predicted this, and Einstein took it seriously. The consequences are shocking. If the speed of light is constant for everyone, then time isn't. Two people moving relative to each other experience time at different rates. A clock on a fast-moving spacecraft ticks slower than a clock on Earth. This isn't a mechanical error. The clock isn't broken. Time itself runs slower for the moving observer. This is called time dilation, and it has been measured with atomic clocks flown on aircraft. The clocks that flew came back showing less elapsed time than the clocks that stayed on the ground. The difference was tiny, nanoseconds, but it was exactly the amount Einstein's equations predicted. Here is a way to feel why this must be true. Imagine you are on a train and you have a clock that works by bouncing a beam of light between two mirrors, one on the floor and one on the ceiling. Each bounce counts as one tick. For you, on the train, the light goes straight up and straight down. But for someone watching the train go past, the light travels a diagonal path up and to the right as the train moves, then down and to the right. The diagonal path is longer than the vertical path, but and since the speed of light is constant for both of you, the longer path takes more time. Your clock, as seen by the outside observer, ticks slower, not because it's broken, because the path of light is genuinely longer. Time itself passes more slowly for the moving observer. This isn't science fiction. GPS satellites must correct for time dilation, both the special relativistic effect of their orbital speed and the general relativistic effect of their altitude, in order to give accurate positions. Without those corrections, GPS would drift by about 10 kilometers per day. Lengths contract, mass increases. The faster you move, the shorter you become in the direction of motion, and the more massive you become. As you approach the speed of light, your mass approaches infinity, which is why nothing with mass can ever reach the speed of light. You'd need infinite energy to push yourself the last fraction of a meter per second. And the fourth paper of 1905 contained the most famous equation in all of science, E equals max squared. Energy equals mass times the speed of light squared. Mass and energy aren't different things. They're one thing measured in different units. A tiny amount of mass contains an enormous amount of energy, because the speed of light squared is a very large number. The c-squared factor is roughly 9 times 10 to the 1690 quadrillion in everyday units. That's why even a tiny amount of mass contains enormous energy. A single kilogram of matter, if converted entirely to energy, would release the equivalent of about 21 megatons of TNT, roughly 1,000 times the energy of the bomb dropped on Hiroshima. In practice, nuclear reactions convert only a small fraction of mass to energy, but even that fraction produces yields that dwarf chemical reactions. That equation explains why nuclear weapons are so destructive, why the sun shines, and why a kilogram of uranium can power a city for a year while a kilogram of coal burns out in minutes. Each of these 4 papers would have made a career. Any physicist who published one of them would be remembered. Einstein published all 4 in a single year, while holding down a full-time job reviewing patent applications. He was 26 years old. He had a newborn son. He had been rejected for academic positions multiple times. and he produced the most concentrated burst of revolutionary physics since Newton's plague year, 240 years earlier. 4 papers, 1 year, and 1 patent clerk. By 1905, Newton's absolute space and absolute time were overturned. The existence of atoms was confirmed. The nature of light was revealed to be simultaneously wave and particle, and the equivalence of mass and energy was established. The 19th century's confident belief that physics was nearly complete looked, in retrospect, like a man standing on a trapdoor and congratulating himself on the sturdiness of the floor. But Einstein wasn't done. Special relativity described objects moving at constant speeds. It didn't include gravity. It couldn't explain why things fall. And Einstein spent the next 10 years working on a theory that could. The result, published in 1915, was general relativity, and it is the most radical reimagining of gravity since Newton. General relativity says that gravity isn't a force. There is no invisible rope pulling the apple toward the Earth. Instead, massive objects bend the geometry of space and time around them. The Earth bends spacetime. The Sun bends spacetime more. A black hole bends spacetime so severely that nothing, not even light, can escape. Objects don't fall because a force pulls them. They follow the curves of bent spacetime. The Moon orbits the Earth because the Earth's mass has curved the space around it into a shape that the Moon rolls along, the way a marble rolls around the inside of a bowl. This was the theory Riemann's geometry had been waiting for. Riemann's metric we covered in the geometry of curved spaces now had a physical interpretation. The curvature of spacetime is gravity. The mathematics Riemann invented for abstract reasons turned out to describe the actual shape of the universe. The equations of general relativity are extraordinarily difficult to solve. Einstein himself could only solve them for the simplest cases. But within weeks of the theory's publication, a German physicist named Karl Schwarzschild, serving on the Russian front in World War I, found an exact solution for the gravitational field around a perfectly spherical, non-rotating mass. The Schwarzschild solution predicted something disturbing. If enough mass is concentrated in a small enough region, the curvature of spacetime becomes so extreme that nothing, not even light, can escape. The boundary beyond which escape is impossible is called the event horizon. The object inside it is what we now call a black hole. For decades, physicists debated whether black holes could actually exist in nature or were merely mathematical curiosities allowed by the equations but prevented by some physical mechanism. The debate ended in the second half of the 20th century as astronomers accumulated overwhelming evidence for their existence. Stellar mass black holes formed from the collapse of massive stars. Supermassive black holes, millions or billions of times the mass of our Sun, sitting at the centers of galaxies. In 2019, the Event Horizon Telescope collaboration produced the first direct image of a black hole's shadow, a supermassive black hole at the center of the galaxy, M87. The image matched the predictions of general relativity. In 2015, a century after Einstein published General Relativity, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected gravitational waves for the first time, ripples in spacetime, caused by 2 black holes spiraling into each other over 1 billion light-years away. The signal lasted a fraction of a second and stretched the 4-kilometer detector arms by less than the diameter of a proton. General relativity had predicted these waves. A century later, they were found. A theory written by a man at a desk in Berlin in 1915, using mathematics invented by a man at a lectern in Göttingen in 1854, predicted the exact shape of an object photographed from 55 million light-years away in 2019. The arc from Riemann's abstract geometry to that photograph is one of the most extraordinary chains of reasoning in human history. In 1919, a solar eclipse provided the first observational confirmation. The British astronomer Arthur Eddington measured the positions of stars near the Sun during the eclipse and found that their apparent positions had shifted by exactly the amount general relativity predicted. The Sun's mass had bent the space around it, curving the starlight's path. The announcement made Einstein the most famous scientist in the world. Let that sink in for a moment. By the end of the 19th century, physics could describe the motion of every planet, the trajectory of every projectile, the behavior of every circuit, and the flow of every kind of heat. Newton handled mechanics, Maxwell handled light, and Boltzmann handled entropy. Together, they accounted for virtually every physical phenomenon that could be measured. The system felt complete. It was not. If you're still awake, what comes next is the part of physics that physicists themselves find hardest to believe. Quantum mechanics isn't just strange. It is, by the admission of some of its founders, incomprehensible. The physicist Richard Feynman, who understood quantum mechanics as deeply as anyone ever has, said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." That is not false modesty. It is an honest assessment. The development of quantum mechanics took roughly 30 years and involved an extraordinary concentration of genius. The physicists who built it were young. Heisenberg was 23 when he formulated matrix mechanics. Dirac was 25 when he wrote the equation that predicted antimatter. Pauli was 25 when he proposed the exclusion principle that explains the structure of the periodic table. They gathered at conferences, particularly the legendary Solvay conferences in Brussels, and argued passionately about what their own theory meant. The photograph from the Fifth Solvay Conference in 1927 is one of the most famous images in the history of science. 29 physicists, 17 of whom were or would become Nobel laureates, including Einstein, Bohr, Heisenberg, Schrödinger, Dirac, Planck, Curie. The development of quantum mechanics took roughly 30 years, from Planck's quanta in 1900 to the complete mathematical framework in the early 1930s. It involved dozens of physicists across multiple countries. Let me trace the core arc. After Planck quantized energy and Einstein quantized light, a Danish physicist named Niels Bohr proposed a model of the atom in 1913. In Bohr's model, electrons orbit the nucleus not at any distance they choose, but only at specific discrete distances, specific energy levels. An electron can be in one energy level or another, but never in between. It can jump from one level to another, emitting or absorbing a photon of exactly the right energy, but it can't exist between levels. The atom is quantized. The idea of quantum jumps was deeply strange. In classical physics, change is continuous. A ball rolling up a hill slows down smoothly. A planet in orbit moves at a steadily changing speed. But an electron in Bohr's atom doesn't gradually transition from one energy level to another. It jumps. It is in one level, and then it is in another level, with nothing in between. No intermediate state, no gradual transition. It's as if you walked up a staircase by teleporting from one step to the next without ever being on the space between them. When an electron jumps to a lower energy level, it emits a photon whose energy equals the difference between the two levels. When it absorbs a photon of exactly the right energy, it jumps to a higher level. This explains why atoms emit and absorb light at specific frequencies, rather than across a continuous spectrum. Each frequency corresponds to a specific jump between specific levels. The colored lines in the spectrum of hydrogen, which had been catalogued for decades without explanation, suddenly had a reason. Bohr's model worked well for hydrogen, the simplest atom. It didn't work for anything more complex. The full theory would require a complete mathematical overhaul. That overhaul came in the mid-1920s, from two different directions simultaneously. The first version came from a 23-year-old German physicist named Werner Heisenberg, who developed it using matrices, arrays of numbers, that described how quantum systems evolve. The second version came from an Austrian physicist named Erwin Schrödinger, who used wave equations. The two approaches looked completely different, but turned out to be mathematically equivalent. They were two languages describing one physics. Heisenberg also discovered something that would become one of the most famous and most misunderstood results in all of science: the uncertainty principle. It says that you can't simultaneously know both the position and the momentum of a particle with perfect accuracy. The more precisely you measure where a particle is, the less precisely you can know how fast it's moving, and vice versa. This isn't a limitation of our instruments, it's a fundamental property of nature. The particle doesn't have a definite position and a definite momentum simultaneously. The uncertainty is built into reality. Schrödinger's equation describes the behavior of quantum systems using a mathematical object called a wave function. The wave function is a mathematical object that encodes every possible state of the system simultaneously. It doesn't describe a definite particle at a definite location. It describes a cloud of possibilities, each with a probability attached. The wave function contains all the information about the system, but the wave function doesn't tell you what the system is doing. It tells you the probability of what you'll find when you look. Before you measure, the system exists in a superposition of all possible states. When you measure, the superposition collapses to a single definite outcome. The measurement problem. The question of what exactly happens when a quantum system is observed remains the deepest interpretive puzzle in physics. Before measurement, the system is described by a wave function that encodes all possible outcomes and their probabilities. After measurement, the system has a definite state. What happens in between? Does the wave function physically collapse? If so, what causes the collapse? If so, what causes the collapse? Does observation play a special role, or would any interaction with a large system produce that collapse? Different interpretations of quantum mechanics give different answers. The Copenhagen interpretation, associated with Bohr and Heisenberg, says the wave function collapses upon measurement and that asking what the system is doing before measurement is meaningless. The many-worlds interpretation proposed by Hugh Everett in 1957 says the wave function never collapses. Instead, at every measurement, the universe splits into branches, one for each possible outcome, and all outcomes are equally real. Pilot wave theory, developed by Louis de Broglie and David Bohm, says particles have definite positions at all times, guided by a wave, and the apparent randomness is an artifact of our ignorance about the guiding wave. No experiment has distinguished between these interpretations. They all make identical predictions for every experiment that has been performed. The physics is settled. The meaning of the physics is not. Schrödinger himself found this deeply disturbing. To illustrate the absurdity, he proposed a thought experiment, now known as Schrödinger's cat. Imagine a cat in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers, the vial breaks, and the cat dies. If it doesn't decay, the cat lives. Quantum mechanics says the atom is in a superposition of decayed and not decayed until someone checks. Does that mean the cat is in a superposition of alive and dead? The thought experiment has become one of the most famous images in all of science, regularly referenced in popular culture, usually incorrectly. Most people think Schrödinger was proposing that cats can be simultaneously alive and dead. He was proposing the opposite, that the idea of a cat being simultaneously alive and dead is absurd, and therefore the quantum mechanical framework that seems to allow it must be missing something. The cat was an argument against the standard interpretation, not for it. Schrödinger wasn't proposing this as something that actually happens. He was pointing out that the theory, taken literally, leads to conclusions that are absurd at everyday scales. The debate over what quantum mechanics actually means, as opposed to what it predicts, consumed some of the greatest minds of the 20th century. Einstein hated it. He believed the universe must be deterministic, that every event must have a definite cause, and that the randomness in quantum mechanics must be a sign that the theory is incomplete. God does not play dice, he famously said. Bohr replied roughly, "Stop telling God what to do." When I first understood that the uncertainty principle isn't about measurement error but about the actual nature of reality, that particles genuinely don't have definite properties until they're observed, something shifted in how I thought about knowing. Before that, I assumed that reality has a definite state at all times, and our job is to discover it. After that, I wasn't sure. The universe might be more like a question than an answer, collapsing into specifics only when someone asks. There is another quantum phenomenon that Einstein attacked, and that experiments have since confirmed: entanglement. Two particles can be prepared in a way that links their quantum states. Measure one, and you instantly know the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance, and argued it proved that quantum mechanics was incomplete, that there must be hidden variables, unseen information carried by the particles, that predetermine the outcomes. In 1964, the Irish physicist John Bell proved a theorem that made it possible, at least in principle, to test whether Einstein was right. The experiments were done, most famously by Alain Aspect in Paris in 1982. The results sided with quantum mechanics. The correlations between entangled particles are too strong to be explained by hidden variables. The particles genuinely don't have definite states until measured, and measuring one genuinely does affect the other, instantaneously, across any distance. This doesn't allow faster-than-light communication. The randomness of the outcomes prevents that, but it does mean that the universe is, in some deep sense, non-local. Things that are far apart can be connected in ways that have no classical explanation. Einstein was right that it was spooky. He was wrong that it couldn't be real. The Einstein-Bohr debates lasted decades and were never fully resolved during either man's lifetime. But the experiments have consistently sided with Bohr. Quantum mechanics, strange as it is, works. Its predictions have been confirmed to extraordinary precision. It is the most numerically accurate theory in all of science. And its central lesson, that the universe at its smallest scales is fundamentally probabilistic rather than deterministic, remains one of the most difficult ideas in all of human thought. Einstein spent the last 30 years of his life searching for a unified field theory, a single framework that would combine gravity and electromagnetism into one set of equations. He never found it. He worked largely alone during those decades, increasingly isolated from the mainstream of physics, which had moved on to quantum mechanics and nuclear physics. His colleagues admired him but considered his quest quixotic. The unification he sought turned out to require not just combining two forces but incorporating all four, plus quantum mechanics, plus the entire zoo of subatomic particles that hadn't been discovered yet. The problem was far larger than Einstein imagined. He died on April 18, 1955 in Princeton, New Jersey. His last written words were equations for a unified field theory, scrawled on a notepad beside his hospital bed. They didn't lead anywhere, and the problem outlived him. But the impulse didn't die. The search for unification, for a single framework that encompasses all forces and all particles, remains the driving ambition of theoretical physics. Maxwell unified electricity and magnetism. Blasio, Salam, and Weinberg unified electromagnetism and the weak force. The hope is that all four forces, including gravity, will eventually be revealed as different aspects of a single underlying reality. Whether that hope will be fulfilled in this century or the next or ever, nobody knows. That is the landscape of 20th century physics. Two pillars: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which describes everything else at the smallest scales. Both are extraordinarily successful. Both are confirmed by experiment, and they contradict each other. Gravity, in general relativity, is smooth, spacetime curves gently, and quantum mechanics is jumpy, probabilistic, discrete. Combining the two, finding a quantum theory of gravity, is the deepest unsolved problem in physics. Nobody has done it. The two pillars hold up the building, but they don't connect at the foundation. Let that contradiction settle for a moment. The two most successful theories in physics, theories that have been tested to extraordinary precision, theories that underpin the technology you use every day, are incompatible with each other. They can't both be right in their current form. One or both must be incomplete, and nobody knows how to fix it. That discomfort, the feeling of holding two contradictory truths and not being able to reconcile them, is the central tension of modern physics. Everything we've covered tonight has been building toward it, and everything that follows exists in its shadow. But before we get to what we don't know, we need to look at what we do, because in the decades following the quantum revolution, physicists built something remarkable: a catalogue of everything. Every particle, every force, every interaction that we've been able to detect and measure, organized into a single framework. It's called the Standard Model, and it is, by any measure, the most comprehensive and precise description of nature ever constructed. The Standard Model identifies 17 fundamental particles. These aren't atoms and made of smaller pieces. Atoms are made of smaller pieces. Protons and neutrons, which make up the atomic nucleus, are themselves made of quarks. There are 6 types of quarks, arranged in 3 generations. The up quark and the down quark make up ordinary matter. Protons contain 2 up quarks and 1 down quark. Neutrons contain 2 up quarks and 1 down quark. Neutrons contain 2 down quarks and 1 up quark. The other 4 quarks, charm, strange, top, and bottom, are heavier and less stable. They appear in high-energy collisions and decay quickly into the lighter quarks. Then there are the leptons. The electron is the most familiar. It orbits the atomic nucleus and is responsible for chemistry, for the bonds between atoms, for everything from the color of a flower to the conductivity of a wire. The electron has 2 heavier cousins, the muon and the tau. Each of the three charged leptons has an associated neutrino, a ghostly particle with almost no mass that barely interacts with ordinary matter. Trillions of neutrinos from the sun are passing through your body every second. They almost never hit anything. You can't feel them, see them, or stop them. That's 12 matter particles, 6 quarks and 6 leptons. They interact through 4 fundamental forces: gravity, which acts on everything with mass; electromagnetism, which acts on everything with electric charge; the strong nuclear force, which holds quarks together inside protons and neutrons and holds protons and neutrons together inside atomic nuclei; and the weak nuclear force, which is responsible for certain types of radioactive decay and plays a crucial role in the nuclear reactions that power the sun. The forces differ enormously in strength and range. Gravity is by far the weakest, roughly a trillion times weaker than electromagnetism. The only reason gravity seems strong is that it's always attractive and it acts on everything. Electromagnetic forces are much stronger but can be positive or negative, so they tend to cancel out in large objects. The strong force is the strongest of all, 100 times stronger than electromagnetism, but it only acts over distances smaller than an atomic nucleus. The weak force is weaker than electromagnetism, and the strong force, and it acts over even shorter distances. Each force has a character. Gravity shapes the large-scale universe, forming galaxies, stars, and planets. Electromagnetism does the work of the everyday world. It holds atoms together, makes chemistry possible, carries light, and powers every electronic device. The strong force holds the nuclei of atoms together against the electromagnetic repulsion of positively charged protons. The weak force enables the nuclear reactions that power the sun and produces the neutrinos that stream through everything. 3 of these 4 forces have been incorporated into the Standard Model with extraordinary precision. Electromagnetism is described by quantum electrodynamics, or QED, developed primarily by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga in the late 1940s. QED describes how charged particles interact by exchanging photons, and its predictions are the most precise in all of science. The magnetic moment of the electron, calculated using QED, agrees with the measured value to better than 1 part in a trillion. That is like predicting the distance from New York to Los Angeles and being off by less than the width of a human hair. The strong force is described by quantum chromodynamics, or QCD. The weak force is unified with electromagnetism in the electroweak theory developed by Sheldon Glashow, Abdus Salam, and Steven Weinberg. Each force is carried by its own set of particles. Photons carry electromagnetism, gluons carry the strong force, and the W and Z bosons carry the weak force. Gravity is the exception. Gravity has not been successfully incorporated into the quantum framework. There is no quantum theory of gravity that has been experimentally verified. The hypothetical particle that would carry gravitational force, the graviton, has never been detected. This is the gap between the 2 pillars. And then there is the 17th particle, the Higgs boson, the one that took the longest to find and required the most expensive machine ever built by the human species. The Higgs boson is associated with the Higgs field, a field that permeates all of space, much like Faraday's electromagnetic field, but with a different function. The Higgs field gives mass to certain fundamental particles, and the way it does this is deeply counterintuitive. Imagine a room full of people standing shoulder to shoulder. If a nobody walks through the room, they pass through easily. The crowd barely interacts with them. That's a particle with little mass. Now imagine a celebrity walks through that room. Everyone clusters around them, slowing them down, making it harder for them to accelerate. That's a particle with more mass. The crowd is the Higgs field. The resistance to acceleration, the clustering, is what we experience as mass. Particles that interact strongly with the Higgs field are heavy. Particles that don't interact with it, like photons, are massless and travel at the speed of light. Without it, the W and Z bosons would be massless, and the weak nuclear force would behave like electromagnetism. The Higgs mechanism, proposed in 1964 by several groups of physicists, including Peter Higgs and François Englert, explains why some particles have mass and others don't. But for decades, the Higgs boson was theoretical. Nobody had seen one. The particle was predicted to exist, but it required energies beyond what any existing particle accelerator could produce. So physicists built a bigger one, the Large Hadron Collider, built by the European Organization for Nuclear Research beneath the border between France and Switzerland, is a circular tunnel 27 kilometers in circumference buried roughly 100 meters underground. Inside it, protons are accelerated to 99.99999% of the speed of light and smashed into each other. The collisions produce temperatures not seen since a fraction of a second after the Big Bang down. Inside the tunnel, superconducting magnets cooled to -271 degrees Celsius, colder than outer space, bend the proton beams around the circular trek. The protons circulate 11,000 times per second. When they collide, the energy of their motion is converted into mass, according to Einstein's E=mc², producing a shower of particles that didn't exist before the collision. Detectors the size of apartment buildings containing millions of sensors record the trajectories and energies of those particles, searching for the signatures of new physics. Thousands of physicists from over 100 countries worked on it. The cost was roughly $13 billion, making it the most expensive scientific instrument ever constructed. The search for the Higgs boson had been going on for nearly half a century. The particle was predicted in 1964, but producing one required collision energies that wouldn't be available until the Large Hadron Collider came online in 2008. Even then, finding the Higgs among the debris of proton-proton collisions was like finding a specific grain of sand on a beach. It required sifting through billions of collisions and looking for the statistical signature of a particle that exists for less than a trillionth of a second before decaying. On July 4, 2012, 2 independent teams working at the collider announced that they had found a new particle consistent with the Higgs boson. The discovery was confirmed over the following months. Peter Higgs and François Englert were awarded the Nobel Prize in Physics in 2013. The 17th particle had been found. The Standard Model was complete. And yet, complete as the Standard Model is, it describes only 5% of the universe. That is not an exaggeration or a metaphor. When astronomers measure the total mass and energy of the observable universe, by studying the motion of galaxies, the expansion rate of space, the patterns in the cosmic microwave background radiation left over from the Big Bang, they find that ordinary matter, the stuff made of quarks and leptons, the stuff the Standard Model describes, accounts for roughly 5% of the total. Another 27% is dark matter. We don't know what dark matter is. We know it's there because of its gravitational effects. Galaxies rotate faster than they should given the amount of visible matter they contain. The extra mass must be there, pulling on the stars, shaping the rotation curves. Clusters of galaxies bend the light of more distant galaxies in ways that require more mass than we can see. The universe expanded and cooled after the Big Bang in patterns that only make sense if there is far more matter than what we can detect with telescopes. The matter is there. We can measure its effects, but we can't see it, touch it, or identify it. Every attempt to detect dark matter particles directly has, so far, come up empty. And the remaining 68% is dark energy. This is even more mysterious. In 1998, 2 independent teams of astronomers studying distant supernovae to measure the expansion rate of the universe discovered something that nobody expected. The expansion of the universe isn't slowing down, as gravity should cause it to do. It's speeding up. Something is pushing the universe apart, accelerating the expansion, and that something constitutes the majority of the total energy content of the cosmos. We call it dark energy because we don't know what it is. It might be a property of space itself. It might be a new field. It might be something nobody has imagined yet. To understand why physicists are so confident about what they can't see, it helps to understand the cosmic microwave background. In 1965, 2 radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, detected a faint hum of microwave radiation coming from every direction in the sky. No matter which way they pointed their antenna, the signal was there. They couldn't eliminate it. They even cleaned pigeon droppings from their antenna, thinking the birds might be the source. They weren't. The radiation turned out to be the afterglow of the Big Bang itself. Light from a time when the universe was roughly 380,000 years old. When the plasma that filled space cooled enough to become transparent. That light has been traveling through space ever since. stretching as the universe expanded, cooling from the white-hot glow of a young universe to the faint microwave hum that Penzias and Wilson detected. The cosmic microwave background is the oldest light in the universe, a snapshot of what everything looked like almost 14 billion years ago. The pattern of tiny temperature fluctuations in that background radiation, hotter spots and cooler spots, differing by less than 1 part in 100,000, encodes an extraordinary amount of information about the composition and geometry of the universe. By analyzing those fluctuations, physicists have determined the age of the universe, the rate at which it's expanding, the total amount of matter and energy it contains, and the proportions of ordinary matter, and dark energy. The precision of these measurements is remarkable. The composition of the universe is known to roughly 1% accuracy. The answer is 5% ordinary matter, 27% dark matter, 68% dark energy. The strongest evidence for dark matter comes not from any single observation, but from the convergence of multiple independent lines of evidence. Galaxy rotation curves. Gravitational lensing, where the gravity of invisible mass bends the light of distant objects. The formation of large-scale cosmic structures, which computer simulations can only reproduce if dark matter is included. The precise pattern of temperature fluctuations in the cosmic microwave background, the faint glow left over from when the universe was 380,000 years old. All of these measurements, using different techniques, different instruments, and different assumptions, point to one conclusion. There is roughly 5 times more mass in the universe than we can see. The leading candidates for dark matter particles are WIMPs, weakly interacting massive particles, hypothetical particles that interact through gravity and the weak force but not through electromagnetism or the strong force. If they exist, they would pass through ordinary matter almost without interacting, explaining why we can't see them. Decades of increasingly sensitive experiments have searched for WIMPs. None have been found. The absence of detection has pushed the search toward other candidates, axions, sterile neutrinos, and more exotic possibilities. The mystery remains open. Dark energy is even stranger. The simplest explanation mathematically is that empty space has a small but non-zero energy density, a cosmological constant, a term Einstein himself introduced into his equation.